Okay, we're going to do our last problem in our review of energy right here. And so I have a sort of a pinball-ish kind of a system. So picture sort of a pinball spring where you pull this thing out and it releases. And the maximum release is when the handle hits that post here. And again, I have a block, so it's not a ball, 0.1 kilogram block. All right. And so the block is on smooth patch, means it's frictionless. So it's released out. And notice that when the spring is released, it's not fully unstretched. So when you pull this thing back, the compression of the spring, I didn't write the number down, just a second, 0.12 meters. And the release compression is 0.02. All right. So there's still a little energy left in this spring. We have to account for that. All right. But the block goes in the meantime, so it's going up and it's trying to get up the ramp. And we're going to ask the question, number one, does it get up the ramp? And if it does, what's its top velocity? Okay. Now, assuming it gets to the top, then the next question is how far will it travel? So anyway, it gets up here, it's along the top, and this is flat. And this is meant to be a rough patch, so it's friction. UK is 0.3. So once it hits this rough patch, gets to here and hits the rough patch, how far along the rough patch will it go before it stops? Then we're going to do the problem again where we say, suppose the rough patch is 1 meter long, so from here to the end 1 meter, and at the end of it there starts a 500 Newton per meter spring. Now the understanding is that underneath the spring there is no friction, okay? So they're not combined, all right? So that's a key point. So we'll let the rough patch stop, and then this spring, it hits it, okay? So these are not combined in any way. So it's followed by the spring. How far will this spring compress? Okay, so we got several things to take a look at. All right, does it get up the ramp? That's a distance. So does it have enough velocity to get up the ramp? That's an energy question. If it does, what's its velocity? So you got distance, velocity, it's an energy question. How far will it travel along the rough patch? Well, that deals with distance and velocity. That's an energy question. How far will this compress? Well, compression causes a force, but when it fully compresses, there's the distance that it compresses it and velocity 0. So these are all very much signs of being energy questions. I bring this up because in the future when there's an exam at the end of the semester, a clue to understanding how to attack a problem, if it's energy, you're looking for something relating distance and velocity. That's just hitting you between the eyeballs what you're looking for. So let's take a look at both of these right now. See if we can solve for a positive velocity, then it must get up the ramp. So in doing that, I'm going to call this right here state 1, and then the top of the ramp, which you're going to see if it gets there, is state 2. All right. So we write down our equation because it just organizes us. It's not hard to do. It's not a big deal. So writing that down. So let's see where we are. So when this thing is here with the spring fully charged, okay, initial velocity is 0. Relative to gravity, potential energy is 0, but relative to the spring, there's quite a bit there. So I'm just going to come down here, so I'll have 0 for the t, and then I'll have 0 for the gravity side, but I'm going to have plus 1/2, 1,000, and it's all charged up, 0.12 meters of compression squared, and there is our potential energy. Between here and getting up to there, there's no motors, no friction, so work done conservative is 0. Okay. If it gets up here, we can say we have 1/2. Okay. Let's see. The block, 0.1 kilogram block, 0.1 V2 for state 2 squared. All right. And so let's see. Then we also have, it's gone up, so we have a potential energy of the block. So that's going to be Let's see what we have. 0.1 kilogram, 9.81 for gravity, and 1.5 for how far the block went up. And now here's the most important part that people would be inclined to forget. Not all of this energy at the start went into the block. There was still some left over. Okay, that's our release compression. So we're just going to take note of that right here. The part that didn't go into anything. Oops. So I'll have 1/2 1000.02 squared. Okay? So that's accounted for that potential energy that still lives in the spring. And this is the potential energy of the block going up. So let's look at what this problem is. There's only one unknown. Here's the thing. If this block could not get up that ramp, when we go to solve for this, we'll be able to solve for it, and we'll get v squared equals a negative number. And you can't take the square root of a negative number. That'll tell you somewhere along here it died. Okay? If we solve all of this and we get v2 squared equals a positive number, it says it made it up the hill, and that's how fast it's going. So, indeed, if you solve for this, I'm not going to go through all the algebra, but you would find v2, v for state 2, is 10.515 meters per second. So, yes, it gets up, and we know how fast it's going. All right, so that takes care of 1 and 2. We'll do part 3 of the question. How far would it travel along this sort of infinite rough patch? Well, so we'll say wherever it ends is state 3. And let's find it. So we'd have T2 plus V2 plus W2 to 3 NC equals T3 plus V3. All right. Well, we know exactly how fast it's going. We have that right here. So 1/2 0.1 kilogram, 10.515 squared. All right. Now, if we look from here to here, we don't care about the spring. And the height never changes, so we don't have to worry about that at all. Okay, so we have for V2, we have a 0. Now we're left with non-conservative work. Well, it's a rough patch, so is there non-conservative work? Yeah, quite a bit of it. It's due to friction, so 0.3. That's our coefficient of static friction, or mass, 0.1 kilograms. Convert that into force by 9.81. And this is going to be negative work due to friction, so it's going to go some distance, and we'll put a minus sign in there because that's what's taking the energy out. On the other side, when it stops, there's no kinetic energy. It hasn't changed height. That's 0, so we'll just put a 0 over here. One unknown, solve for D. And we would get 18.78 meters. All done. Part 4 says, suppose the rough patch is only 1 meter long. So same problem, but now this piece here is only 1 meter. Do it again, where we wind up hitting this spring. So let's make that happen. So I'll go from 2 to what I will call state 4 over here. So T2 plus V2 plus W2 to 4 equals T4 plus V4. All right, T2, the speed at the top of the ramp is the same. So I have for T2 1/2 0.1 10.515 squared. Initial potential energy. Well, let's see what we have here. The height stays the same. The spring would not be stretched yet or compressed. So there is no potential energy to be concerned with. Now we have our non-conservative work. Put my NC in there. And that's the rough patch over 1 meter. Okay. Coefficient of friction, 0.3. 0.1 kilogram, the mass. Acceleration. And it goes 1 meter, but it's friction, so it all is negative. It takes energy out. Go to the other side. Kinetic energy. When this is fully compressed, at the spring, there will be no velocity. There is no change in potential energy due to height, so I'll put a 0 for that. We're just left with the potential energy change as the spring is compressed, and we don't know what that is, so that's 1/2 500 newtons per meter x squared for whatever that compression is. If we solve for that, according to my notes, this is 0.14, I think, 5 meters. Oh my, you haven't been able to see that. I'll leave that here for a moment for you all to take a look at it. And next time we talk, we're going to be moving on to another topic. Have a great day. If you're having any problems following this problem, because the back part was hidden for a period of time, take a screenshot of this at the end right now and go back and listen to the last few seconds of the video comparing them. You'll have it. All the best. Bye.